Well, thank you all for attending. I think just for time, we'll get started and hopefully other people will kind of join as we get going. Thank you again. This is our second in our series of 3 webinars from Rocky Mountain ACSM. I'm Ben Thompson. I'm the past president of the Rocky Mountain regional chapter of the American College of Sports Medicine. Thank you for joining us this evening. Before we introduce our speaker, just a couple quick things. So question and answers. So the chat is going to be reserved for question and answers. And I think we're going to keep those to the end of the lecture so we can go over those. And then once you leave the meeting, you'll get a short email asking for some feedback. If you could please just fill that out for us, we would greatly appreciate it. Other than that, I will pass it off to Nellie Brunge, and she's going to introduce our speaker.
Thanks, Ben. Good evening, everyone. Thanks for joining us here for the second installation of our Winter Olympics themed webinar. It's my honor and pleasure to have Dr. Stephen Cheung join us here tonight. It's a very fitting night for his talk here in snowy, cold Wyoming. So we're honored to have Dr. Cheung join us. He is a professor and senior research fellow at Brock University in Ontario. He did his training at the University of British Columbia, followed by a master's at Simon Fraser University and a PhD from the University of Toronto. He's really and truly a leading expert in the field of environmental and cold physiology. In fact, he's literally written the textbook that many programs use across the country here in the United States, and I assume up in Canada. In fact, our graduate class here at UW, I know for a fact, utilizes this textbook. So we're really excited to hear from him tonight. So please join me in electronically welcoming Dr. Cheung to tell us a little bit about performance impact in the cold.
All right. Thank you for that introduction, and thank you for the opportunity to speak. So Nellie, can you just confirm that you're seeing my PowerPoint slide? Okay.
You look fantastic. Yep.
Excellent. So again, thank you for the honor of speaking to you, and thank you for your attention in advance. I hope you all have some leftover Halloween treats like I do, because one of the things we will be talking about is, even though we're exercise scientists, we're supposed to stay away from processed sugar. Sometimes that is a good thing to have in cold settings. So we will talk about that. Title of my talk is The Performance Impact of Cold, and we'll be taking a look at a number of topics within that. Specifically, this talk is going to cover 4 major questions and try to touch on each of these about some of the things that we know. A lot of them have come from research in my lab and over the number of years. So the first question I'll try to address is, does mild hypothermia reduce exercise performance? Does an actual drop in body temperature lower your exercise capacity? The second thing is, those of you who have been cold, and I'm sure that includes everyone, know that one of the first responses of the body is to shiver. So we'll talk a little bit about the mechanism of shivering, and also especially its impact on metabolism and the metabolic cost of shivering. We'll then diverge from there to, what do we know about sex differences in response to cold exposure and to hypothermia? Short answer, very, very little research. And then the last one is kind of a pun title that we have, but it's really talking about, can we use nutritional supplementation or nutritional intervention to prevent cold injuries in the extremities, in the hands and in the fingers? And specifically, can we use beetroot juice or supplemental nitrate to increase blood flow to the extremities? So those are the 4 major questions that this talk is going to address. So the first question is, again, does mild hypothermia reduce exercise performance? Now, again, surprisingly, this is the general theme I'm going to be talking about throughout, is that in environmental physiology, there's getting to be a lot of work on heat physiology, on exercise in very hot environments like we just had with the Tokyo Olympics, and a plethora of research there. compared to the amount of heat physiology research, there's relatively few research done in actual cold and specifically in actual hypothermic situations. And even the work that has been looked in cold, a lot of it recently has been in the context of pre-cooling. So if we know that we're going to be exercising in the heat, we're going to cool our body down, whether it's with towels, with wet towels, with ice slushies, with water baths, etc. And then we're going to perform in the heat. Again, relatively little work has actually looked at body temperature dropping by 0.5 degree to 1 degree and then actually exercising in the cold. So in 2018, my master's student, Steve Ferguson, and I addressed that, and we looked at the question of, does exercise performance in a time trial situation become impaired if our body temperature is dropped by 0.5 degree Celsius, and if we are exercising in a cold environment in 0 degrees Celsius air? So that's 32 degree Fahrenheit. So that was our first two conditions. So we had either of them in a neutral room temperature, 23 degrees Celsius, and then they did a 15-kilometer time trial. The second condition was they were in a 0 degree Celsius chamber, just wearing your typical cycling gear until they dropped 0.5 degree core temperature. And then they jumped on the Velotron bike and then did a 15-kilometer time trial while the chamber was still at 0 degrees Celsius. So there's your basic stock standard kind of a control and experimental condition. The third condition was a cold and hyperoxia condition, where they were again cooled by 0.5 degree core temperature and then jumped on the bike in 0 degrees Celsius. But instead of breathing normal kind of ambient air, they were breathing hyperoxic air. This was blinded to the participants, but they were breathing 40% O2. The reason we wanted to do this particular condition was we want to see if, as we expect, there is going to be an impairment in cold. Is it because their temperature is actually cold, or is it possibly because of reduced O2 availability, because of vasoconstriction, because of reduced muscle and skin blood flow? So the idea here is that by giving them hyperoxic air, they are going to compensate. They might still be vasoconstricted, but the muscles will still get greater oxygen availability because of the enriched oxygen content. So that's the three conditions that we had. So the first thing that we wanted to see was, okay, if there is O2 kind of a supplementation, is there a thermal benefit? So we see this, let me just change my laser pointer. So we see this up top, we have the core temperature and we have the baseline during the cooling and then just before they start, and then every 2.5 kilometers during the 15-kilometer time trial. Not surprisingly, in both cold conditions, their core temperature was lower. Their skin temperature on this bottom graph was also lower, and it stayed significantly lower than if they were in the neutral condition. So our conclusion from these graphs and these data is that we did achieve the thermal manipulation that we wanted to, and also that hyperoxia did not have a thermal benefit because we saw no difference in the cold versus the cold plus hyperoxia in terms of temperature. The second thing that we looked at was, okay, did we achieve our second goal of the hyperoxia, hopefully restoring O2 or increasing O2 availability? So this was with finger pulse oximetry, and we were looking at, again, O2 saturation during these different intervals. And we see that with both the neutral and the cold during the time trial, oxygen saturation decreased over time, whereas with the cold plus hyperoxia trial, we maintained O2 saturation at near 100% throughout. So Overall, our manipulation seemed to have held, that we dropped core temperature, and also that we maintained in the cold plus hyperoxia trial increased O2 availability. So then what were the brass tacks? What actually happened in the 15-kilometer time trial? So we have power output on the left here. So we'll focus on that. And what we see is that with the neutral compared to the cold, the cold compared to the neutral had a significantly lower power output. So roughly about 15 watts lower on average throughout the entire 15-kilometer time trial. And then when you're in the cold plus hyperoxia condition, the time trial performance and the power output was maintained back to what it was at neutral. So our overall conclusions from this study was that there was a 0.5 degree Celsius hypothermia. It does impair time trial performance. And then secondly was that hyperoxia did not change anything with the thermal profile. And however, it restored performance. And our proposal based on our research design and our data is that the mechanisms by which it did so was O2 availability. And so therefore, we suggest that the reason why your performance is impaired in the cold may not necessarily be because of, for example, a central drive from our brain, but really down to reduced O2 availability because of vasoconstriction in the cold. Okay. So that was kind of looking at the whole body in a hypothermic state. The next series of studies that we did then looked at the individual muscle itself. And these were the next couple of studies I'm going to talk about were PhD projects for my student, Matt Millett. And the specific protocol that we had was we had a brace with a force strain gauge, and they were asked to do an isometric wrist flexion. So they were asked to try to do this, but obviously in an isometric mode. And then instead of using just traditional surface EMG, we used a decomposed EMG to look at the individual. And for those of you who aren't familiar with decomposed EMG, it is kind of like surface EMG, only kind of it tries to take it from the more multi-electrode kind of 3D type of idea by having multiple electrodes and then using math to break it down into individual motor units. So what we did then was we had in either with the muscle, so we were focusing on the FCR, the flexor carpi radialis, and we were again asking them the wrist flexion, and we're measuring the decomposed EMG. We asked them to perform that task at 30% of their maximal voluntary contraction, so 30% of their MVC. And then what we have is the neutral graph on the bottom and the top graph on the cold. And again, for those of you who aren't familiar with decomposed EMGs, this is a typical kind of graph that you can produce from it. And what it is looking at is the number of motor units. So each of these bands are individual motor units. And then it's also recording when they are firing, the onset of firing, and also the cessation of firing. So we have the neutral figure here. And then we have the cold, and we did the cold by cooling the muscles for 20 minutes with a cooling kind of bath. So the main thing I want to point out from these two graphs are the following. So if you look at the y-axis, you'll see that in the neutral, there were 14 motor units that were identified as firing. In the cold condition, there were 17 motor units. So the body, to perform the same task, required more motor units to do so. The second thing that we can observe on here is that the motor units had to be recruited beginning earlier, and also they had to be recruited for longer. So if you look at each of these individual kind of circles, they represent the motor units and when they began firing. So the overall pattern is that in the cold, not only do you have to recruit more motor units, they had to be recruited for a longer period of time to maintain the same absolute force. So then following this, we decided to then look at, okay, we saw that pattern in the muscle, but can it maintain kind of this similar level of accuracy, even though they were in essence requiring more motor units to do more in order to do that work? Can they actually maintain the muscle accuracy? So for the second study from Matt, we developed a jury-rigged cooling sleeve consisting of Tygon tubing with cold water or hot water running through so we can control the temperature. Compared to the first study, this was a much more elegant and controlled setup because we could maintain the temperature around the forearm, both during the cooling phase and also during the testing phase itself, as opposed to when we put just our forearms into cold water and then we go into air and put it on a brace. By the time you do the testing, obviously the muscle and skin temperature could be changing. So this was how we did it the second time. And you can see there's our thermocouple and then also our EMG electrodes. So for this one, we used, again, we used a kind of a step pattern, and we had them perform the isometric wrist flexions at 10. Let me actually show the data here. At 10% MVC, 20% MVC, 30%, then down to 20, down to 10, and then rest. And this was the force profile. So we were really looking at, can they maintain that level of force with similar levels of accuracy? And this graph is the coefficient of variation of those stair-step patterns. The main message here is that whether your forearm muscles were heated up or if they were cooled, the coefficient of variation of that force was very similar. So these were the actual mean data, and these were representative tracing. So you can see there's a very tight kind of accuracy within that. It wasn't as if when they were cold, they were all over the map in terms of fluctuating during the each individual step. So our conclusion then is that more motor units are being recruited for longer time, but the level of accuracy of force production remains similar. Now, the key thing to keep in mind is that looking at this, this figure here, this photo on the left, we can see that we did not cool the wrist, did not cool the hand. So there were no changes in kind of manual dexterity or kind of, or both kind of gross dexterity with the wrist. So, you know, if you're now in less than 100 days time looking at the biathlon in the Olympics, this doesn't necessarily apply to things like marksmanship. We're really looking more for large muscle, a relatively large muscle. We weren't trying to make any extrapolations about manual dexterity or kind of fine control and accuracy with our fingers. Indeed, we want to eliminate that in this study. Okay, so the summary for the first question, based on the research that I've shown so far, is that first off, even mild core cooling does form an increased strain on our physiological capacity. The core cooling decreased our 15-kilometer time trial performance. And our hypothesis or proposal for why this happens is that there is a diversion, or kind of the muscle is trying to do two things at once. It is both trying to, shiver possibly, but also it is trying to, the body is trying to vasoconstrict the peripheries to favor the core. So there is an O2 competition with thermal regulation versus actual muscle activity. And then based on the PhD projects from Matt Millett, we conclude that cold muscles have to work harder. Again, we require more motor units to just do the same work. However, it seems the accuracy of that work can be maintained. So the second point, or second major theme I want to raise, is what is kind of the mechanisms and what is the cost of shivering? How is it being fueled mechanistically? And this is where you might want to start getting your Halloween leftover treats out. So what is shivering? So the thing we shouldn't, or sometimes people think that shivering is just this constant action throughout the body, that, you know, we're just both contracting our muscles constantly and at the same rate, both over time and also over the different muscles in our body. And that is not true, based on work done at the military lab in Toronto, where I did my PhD. And these studies were published just before I kind of showed up as a PhD student. But Doug Bell and Peter Tequisis did these really nice studies where they had EMGs on different parts of the body, and then really tried to calculate the relative percent of contribution of the different muscles to heat production. They also looked at the kind of the recruitment of muscles on shivering. So they found that it was really kind of from the torso outwards. So most of the shivering began in the jaws and also in the trapezius muscles. Then it kind of went into the pecs and the core, and then it kind of branched outwards at the end in terms of the onset of sustained shivering. So what Doug Bell found was that there was a spatial pattern in intensity, and that overall the intensity of the contractions varies depending on the muscles, but in the trunk, it can be anywhere from 8 to 16% of maximal voluntary contraction at really high levels of shivering, whereas in the peripheries, it is lower at 4% roughly of MVC. And again, in terms of heat production, if you look at the graph or the figure on the left, about 70.5% of total heat production, according to their calculations, comes from the trunk, comes from the rectus abdominis and the pectoralis major. Whereas again, as you go from the proximal limbs to the distal part of the limbs, there is again less and less shivering as we go further from the core. If we're looking at from it teleologically, this also makes sense that the priority is really maintaining the vital organs in the torso and then getting back to the brain. Peter Tequisis's contribution to it was also looking at kind of two groups. They had them separated by relatively, and these were all males, relatively lean body fat of less than 11%, with another group that was doing this that was at a higher body fat. And they found that in general, you know, there's a lot of inter-individual variability, but in general, the lower body fatness you had, the leaner you were, the greater the metabolic rate, the greater the rate of shivering. And this happened both in terms of an earlier onset of shivering. So you started shivering at a higher threshold for both skin and core temperature, and you also increased the intensity. The other thing is, you know, does shivering actually cost energy? And this was coming from work from Dominique Gagnon, who was a Canadian who did his PhD in Finland, and I was part of his PhD projects. But what he was more interested or mainly looking at what happens if you were already shivering, how does that impact kind of your metabolism during exercise? So that was kind of the basic outline of what he was trying to do in his PhD papers. However, in this particular paper in 2014, he had individuals either, you know, not shivering beforehand or else cooled down in, again, 0 degrees Celsius air until their shivering was relatively stable and moderate at about 40% of their peak shivering. So this is already pretty uncomfortable. You're starting to bounce around quite a bit in your chair. Then he had them exercise at either 50% of their VO2 peak or 70% VO2 peak. So relatively low and a relatively moderate exercise intensity. And the way he did this was what was unique and what I want to highlight here rather than the metabolic parts. What he looked at here was he had them on a treadmill where It wasn't at a set speed. So it was a VO2 clamp protocol that he had, that whether they were in control condition or whether they were in the shivering condition, when they were in the 50% VO2 peak or low exercise intensity, that was what was clamped. So it was possible that the speed of the treadmill was adjusted so that the actual oxygen uptake was identical, whether they were not shivering or whether they were shivering. So then from the perspectives of this talk, the main data I want to highlight is what were the treadmill speeds over time in those two conditions. And we see that in the low exercise intensity condition, when you were shivering, you were walking at just a bit over 5 kilometers an hour, whereas when you were in control, you were at about 6.25 kilometers an hour. And then this was true at 30-minute time point also. When you're in a moderate intensity exercise, the same pattern held over the first 15 minutes, that when you were shivering, you were walking at a lower speed to achieve 70% VO2 peak. So the main kind of conclusion to draw from this is that there is an O2 demand to fuel shivering. So if you know you're going to be out in the cold, you cannot, and that your body temperature may be dropping, you can't expect to work as hard as you can when your body temperature is normal, because if you are shivering, that is obviously costing oxygen to fuel that shivering rather than actual kind of synchronized mechanical movement. So then the next question is, okay, so there are challenges with shivering, but how does this impact our fuel use? So I've put together, and this is a figure from the textbook, I put together two different experiments into the same graph. So let's talk through them. The upper part here is looking at the data from Weber and Hamann, and what they looked at was high intensity shivering. So this is about 3.5 METs. So this is really starting to get intense in terms of shivering. At very, very high maximal shivering, you may be at about 4 to 5 METs of oxygen uptake. So this is really, really bouncing off the wall. So what we have here is the relative contribution of carbohydrates and lipids to fuel that high intensity shivering. And the main thing I want to highlight is at that high intensity of shivering, the relative contribution of carbohydrates to fats is pretty similar to what we find when we are just normally exercising, when our body temperature is normal, when we're doing moderate exercise at 70% VO2 peak. So very similar kind of. So for that, even though obviously the actual metabolic rate here is lower with shivering, there is already quite a shift towards carbohydrates. So that can lead to the question of, and this was the traditional thought until relatively recently, that we can be in a lot of trouble if we run out of carbohydrates, if we essentially bonk and run out of carbohydrates in our blood and also glycogen stores, that we may not be able to fuel high intensity shivering anymore, and therefore we may become fatigued and stop shivering, in which case we're going to get even colder, even faster. However, let's take a look at this bottom graph, and what this shows is an experiment where they had starting glycogen levels either very high, super compensated, normal, or low. So the interesting thing here, the intensity of shivering was lower. Instead of 3.5, it was 2.3 METs. What they found here was that if the carbohydrate and the glycogen stores were low, it seems that the body is able to compensate by shifting from primarily relying on carbohydrates to fats. And that is really good news for us if we're exercising in the cold, performing long duration expeditions in the cold, and also for survival modeling for search and rescue. If we know that based on this data, the body seems to be able to adjust its fuel use based on glycogen availability to maintain shivering at its desired rate. So that is good news for, again, thermal modelers and survival models. So related to that is, okay, what happens if we're not just have low carbohydrate stores, but we are also heavily exercising? And this was another study done by Peter Tequisis. This was just done, unfortunately, while I was a PhD student at the military lab in Toronto. So of course I was a participant for it, but this was definitely, as a participant, the worst study I was involved in. So obviously we had a control condition where we were normally fed, did not do any exercise, but the experimental condition was 5 hours of aerobic and resistance exercise. So we had an hour of rowing, then an hour of hard weights, an hour of cycling, an hour of hard weights, and then an hour of slow jog. And throughout, we were not eating, so our glycogen was also being depleted. We only had water to maintain our body mass. So that was just the first part of the study. Then the fun really began, because then we spent up to 4 hours in a 10 degrees Celsius chamber, just wearing swim shorts. And to get the full experience, we also had a 10 degrees Celsius shower spraying on us with a 6 km/h wind. So yes, this was exactly as uncomfortable as I'm making it sound, possibly even more. So on the left here is a very appropriately named survival curve that you have seen before, but in this case, it is a highly, highly appropriate. So we had 30 minutes of baseline and then up to 4 hours of exposure. So this was the control in the solid lines and the fatigue condition in the dashed lines. So overall, even though there was about a 25-minute lower tolerance time overall for the fatigue condition, the statistics suggest that overall there was no significant impact on kind of tolerance with heavy exercise. And I know Dr. Andy Cheung has done work with US Army Rangers during training in the 90s, where he shows over the period of Ranger training, there was, at the end of that long period of multiple weeks, that there was a significant impact on thermal regulation. Again, the difference here is this was one acute trial. And again, looking at the p-values, it's very close to significance. And also there was a huge amount of inter-individual variability. I know if you ever look up this paper, I will put my hand up and break confidentiality. I was participant 9. You can see that my data, and I recall my data is quite dramatic. I believe I was about 35-40 minutes lower tolerance time when I was cold. So huge amount of inter-individual variability. And this was something that Peter then followed up with in the same paper. He looked at whether kind of you could predict survival or tolerance based on body fatness or metabolic rate or aerobic capacity. And he found that, and again, this isn't necessarily surprising, that people with high body fat were able to last longer in the cold. People with a high shivering rate were also able to tolerate cold longer. However, there was no significant kind of prediction based on VO2 max. So overall, from Peter's study, it suggests, combined with the other data I've shown, that fatigue and glycogen depletion likely did not impact cold tolerance. Again, given the caveats of what I said compared to the US Army Ranger data of much longer period, and also with sleep deprivation. And the main thing that Peter also contributed is, again, that body fatness and shivering intensity were strong predictors. And this is still kind of somewhat of a challenge, trying to understand whether, you know, I, who am relatively lean versus someone else, how we're gonna tolerate cold. And, you know, it makes it really hard, again, to develop survival models based on on, is it just purely just body fatness, and what else might be predictors. Okay, which leads to, that was the most miserable study I did as a participant. Now let's move to the most miserable study I asked people to do as a researcher. And this was we did this study about 10 years ago now. And this was funded by Search and Rescue and the Coast Guard in Canada. And they were trying to model Arctic survival. So keep in mind, again, with most of these survival models, they are really based on data like Peter's, which at a very extreme was 4 hours. And most hypothermia studies are 2 hours or less. So we're taking data from humans responding over 2 to 4 hours, and then we're trying to extrapolate them over to as much as a week that it might require if there was an Arctic survival situation of a mass rescue, whether it's a plane crash, whether it's a cruise ship that runs aground. Even in good conditions, it might take up to 5 to 7 days to affect a mass rescue like that. So again, the challenge is 2 to 4 hour data on humans, trying to extrapolate that to a week. So we tried to push the envelope in this study by having a 24-hour survival simulation. And so we had participants in 7.5 degrees Celsius air, just wearing short sleeve cotton coveralls, and they were eating survival rations, and they had minimal kind of stimulation. They were in pairs, but they just had a deck of cards like you might in a survival situation. So they were eating your lifeboat type of survival rations, really, really horrible, and only 500 mils of water. The whole goal was that we did not want to have them drop out due to actually become overly hypothermic, because then we wouldn't get the 24 hours. The 24 hours of moderate to sustained shivering was our priority. So to do this, we dropped their core temperature roughly about 0.5 degree to 1 degree Celsius throughout, and maintain that for 24 hours. Again, as uncomfortable as you can imagine. So our secondary hypotheses were, will the participants kill me? And then our third hypothesis was, will my students kill me? This was about a 40-hour continuous trial to run one through, not including kind of all the practice and pilots. So here's the main data that we produced from here. And again, there is good news, and it matches what I have kind of suggested before, that the body is actually quite capable of sustaining shivering throughout. And if you look at the heat production, which is on the right graph and in the dashed lines, we see that over the course of the 24 hours, and this went from roughly about noon to 1 p.m. kind of start, we staggered the participants in so that we could perform all the testing. And then through the night, and then again throughout the next day till noon, they were able to not just maintain their shivering and heat production, but they were actually able to increase it over time. And the way this was fueled was as suggested by the kind of more acute data that we saw before, that the body after about between 6 to 12 hours seems to shift towards a greater reliance on lipids for fueling the metabolism of shivering. So our conclusion was that shivering was likely sustainable through prolonged exposure and fatigue. So to summarize this part of the talk, we conclude that shivering is effective, but does come at significant kind of metabolic cost. It is potentially as demanding as the equivalent exercise, but there is an even greater demand on carbohydrates, at least to start. But overall, long-term use and long-term exercise, there does seem to be this shift from carbohydrates to fats. And again, that has huge implications for survival modeling, for extended expeditions, for fueling kind of extended kind of survival situations, extended expeditions out in the cold. The other thing that we conclude from here, the other thing is that it doesn't, in a sense, seem necessary that we need to emphasize in these kind of long-term expeditions or in a hypothermia and survival rations. We don't seem to require a heavier reliance on carbohydrates in that survival ration. We just need more calories. We just need enough calories, and it can be in the form of fats, and that the body can manage that and fuel shivering regardless. So then the third aspect that I want to talk about is sex differences in cold response. This part is going to be very brief because ultimately there's very, very little research. There is only now starting to be more research on sex differences in heat response, but there's almost nothing on cold response. So what there is equivocal. There's, again, only maybe about less than half a dozen studies, and half of them show there's some difference, half of them show there isn't a difference. In the there is a difference side of the equation, we have this study where they used a thermal blanket with water tubing kind of running through. Essentially, think of it like a sleeping bag, but with water pipes running over your skin. And they had males and females of similar BMI, but different body fat in there. And then they gradually dropped the coolant temperature in that thermal blanket. And they were looking at when do individuals start shivering, and also what was their sensation of cold at different kind of blanket temperatures. So the main result that they saw was that females had shivering initiate at a higher thermal blanket temperature, so roughly between 11 and 12 degrees Celsius. Whereas if you look at the males, the average was much lower at about 9.5. And I'll just note that they capped the floor at 8 degrees Celsius. So they didn't go to 7, 6 degrees, etc. So if you went to 8, you stayed at 8, even though, as you can see, the vast majority or the majority of males were able to reach 8 and probably could have reached lower. So this data, if anything, is skewed towards being more similar than it is. So their conclusions from this study is that females have an earlier kind of skin temperature or onset of shivering. And then when they looked at the perceptual data, that there was a greater cold sensation at each kind of equivalent temperature at, say, 13 degrees or 12 degrees or 11 degrees. So then what is kind of the data? What are the data looking at the opposite, saying there is no difference? This was another study from Peter Tequisis about 20 years ago. And in this study, they had females and males in 18 degrees Celsius water up to the neck for 90 minutes. The thing to note is there was no kind of oral contraceptive kind of a questionnaire. So no knowledge of oral contraceptive use, and also no control for menstrual phase. So they just took females and tested them at any random time. And this was the core temperature data for the males and also for the females. And then here is the data for shivering or metabolic rate for, again, the males and the females. So it seems that there is a difference here in the cooling rates and in the metabolism for males and females. But what Peter suggests that when you remove and normalize the differences in body fatness and body size between males and females, that these differences were washed out. So his conclusion remains that body fatness and body size were more important to your cooling rate than sex itself. This was another study from Denis Blondin looking at now menstrual cycle effects on shivering. So they were using a cooling suit like you see with NASA, and some of you may have in your labs, of skin-tight clothing with water tubing running throughout, and they performed cooling with much tighter oral contraceptive control of all testing non-OC users, and then testing them at the follicular phase and also the luteal phase. What he found was that the shivering pattern was similar across the follicular and the luteal phase. In terms of burst intensity, was the same at about 6 bursts per minute. There was also no difference in shivering intensity. It was quite intense at 14% MVC. Remember I said earlier on with the Bell and Pequesis papers, they were showing anywhere from 8 to 16% MVC. So this was quite intense shivering, and they were capable of equal kind of shivering intensity, both in the follicular and the luteal. Looking at the heat production on the top, the oral canal temperature, so with a direct thermocouple, and also with skin temperature, again, no difference across the phases. So this was a study that would suggest that there is no effect. And this is work that I would like to follow up with more. And I have a PhD projects going on right now with cooling in the cold, and again, exercise capacity and cognitive capacity. And I would definitely be recruiting females there too, and ideally females at different phases of the menstrual cycle to look at this further. So the main conclusion is, we don't know. I've pretty much talked about 50% of the studies that exist in this field. So lots more research is needed. The last thing is a PhD study from my student Kate Wickham that I want to talk about. We just published it earlier this year. And again, the idea is, can you use beetroot juice and nitrate supplementation to improve the finger blood flow in cold exposure? With the idea that, as many of you know, it's been in all the news and lots of papers coming out on it in terms of beetroot juice as a vasodilator, as an improvement in cardiovascular health, reduction in blood pressure, improvement overall in vascular tone. So we want to see at the microvasculature, and especially at the fingertips, does this have a benefit too? So before we look at that, I need to talk about this idea of cold-induced vasodilation. Now, most of you, again, I heard Wyoming just had its first snowfall. If you're now out walking around without gloves, your hands are probably feeling cold. But one of the things after about 5-10 minutes you may notice is that there's this paradoxical sensation of warmth in your fingers, and then it fades again, then it might come back again. And this is called cold-induced vasodilation. This was first discovered or reported in 1930 by Sir Thomas Lewis. And to this date, we still don't really have a strong handle on the underlying mechanisms. We know that it mainly occurs in the glaber skin, or the hairless skin of the fingers and the toes, and some on the nose. There's theories of, because we see this warming and rewarming and kind of cooling and warming again, there's some ideas that it's protection from freezing or non-freezing cold injuries. And, so it's been of special interest from the military to try to minimize frostbite risk in soldiers. We have shown with Carla Gertz in 2005 that the episodes of CIVD does not impact neuromuscular function of the hand. We tested the neuromuscular kind of capacity and characteristics of the hand muscles during the trough and the peak of CIVD. We found no differences there. The other challenge is that it's not really predictable across individuals. I definitely cannot just look at someone and say, oh yeah, their hands are going to be fine in the cold, whereas another person's going to be really at risk in the cold. There's some really broad general kind of rules of thumb, but they are incredibly broad, and it's almost impossible to just predict an individual's response. The other question is, can this be trained? Again, there's a lot of military emphasis on both supplements and also training to improve CIVD, so that ideally it can protect soldiers operating in the cold. Overall, the survey of studies that are done in the lab suggests that it can't. There's only one existing study, and that was from 1962, that shows there's been any benefit, and that one had almost 6 months of constant daily exposure. So it's almost completely unrealistic in terms of performing. There is some evidence of possible long-term trainability in the field. Some of it came from looking at Indian military from the southern plains of India, who then go to the Arctic for Arctic exercises, and showed that after about 4 to 6 weeks, there were improvements in finger blood flow and finger skin temperature. Okay, so to get the Kate study, what we looked at was, again, we had either beetroot juice or we had a nitrate depleted placebo. So it was otherwise absolutely identical. And we had them ingest it and then wait 2 hours. And then we put their hand in 8 degrees Celsius water for half an hour. So what we have on the left is the mean arterial pressure over the 2 hours of after ingestion. And this was mainly just to show that the beetroot juice did have an effect, that it systematically lowered mean arterial pressure quite significantly in the 30 minutes and right before we put their hands in the cold. So what did we do? We used a laser Doppler flux meter to measure actual finger blood flow in the, again, in the nail bed, in the fingertips. And we looked at it over the entire half an hour of exposure, and we integrated all of the rises that we saw into an area under the curve. So we summated all of the kind of the blood flow changes into an overall thermal profile, so to speak. The main conclusion is when we were looking at area under the curve with placebo or nitrate ingestion, we found no difference in the area under the curve. We also found no change in any of the traditional CIVD parameters, such as the time to onset, the amplitude of a CIVD signal, the duration of a CIVD signal, etc. So in summary, our overall kind of a lot of the work that I've done on CIVD suggests that it's really hard to predict. We still don't really know for sure the mechanisms for it. There's a few kind of key mechanisms that have been isolated. Some studies suggest it's one path, some suggest that it's another. We do see that it doesn't seem to be lab trainable in a realistic setting anyways. The challenge is, again, the risk prediction is really difficult. And then there's also been work looking at the combination, not just cold, but hypoxia, because obviously for mountaineers, they're going to be in a hypoxic and hypobaric situation also. Our main conclusion from Kate's research is that dietary nitrate had a systemic change in cardiovascular effects with the mean arterial pressure, but it didn't have a change in the microvasculature at the finger blood flow itself. So with that, I will thank you again for your attention. I want to thank again the Rocky Mountain ACSM for inviting me, and hope you found that this talk was pretty cool. And I'm happy to answer any questions. As you see up top there is my textbook, and the second edition just came out this April. The first edition came out in 2010, so I spent part of my sabbatical really working on in 2018, 2019, really getting the proposal going and really starting to overhaul it. And so I'm really proud of the results. There's actually 5 new chapters of topics that, to show how quickly the field progresses. There were 5 new chapters in this edition of topics that weren't even there 10 years ago. So there has been quite a change in the field. And as you see, I also, even though I personally get cold really quickly, and I often, my family laughs at how intolerant to cold I am, I still like being out there and being active. So again, thanks, and I'm looking forward to any questions.
Well, thank you, Dr. Cheung. That was wonderful. It sounds pretty horrible, some of the things that your subjects were. I hope they got compensated, but thank you very much for that. We actually do have some questions. So Nellie, do you want to read those, please?
Yeah, sure. So go ahead and keep putting those questions in the chat. Thanks to those of you who have already. So our first question is, what is your process for breaking down a systemic environmental response to an individually testable hypothesis?
Okay, so let's take an example of again, let's take this question of how I approached the the first study that I talked about, the Ferguson 2018 study on exercise in the cold. So I guess the first thing is when Steve Ferguson and I were trying to come up with a good master's project was, we were really just trying to answer the question and look for gaps that are out there. And one of them was really, there's so little work done on exercise kind of in the cold environment, really in a controlled cold environment. So that was the avenue that we went down. And then we kind of targeted further. Okay, well, we're already going to do a neutral in a cold condition. Can we think of something else to add? And that's where we got the hyperoxia, kind of really looking at the oxygen angle. And a lot of it is also just serendipity. I'll take an example from kind of the research that I've done to CIVD. And I remember this was during my first sabbatical in 2005 when I was in Europe in Slovenia with my former master's advisor and Igor Mikjavich. And we went to a NATO-sponsored symposium about, soldiers and cold injuries that was held in Amsterdam. And we were sitting there and I'd already done some work in the field before, but we were sitting there and talk after talk after talk, testing CIVD, had individuals essentially stick one finger into kind of cold water, whether it was 2 degrees Celsius, 5 degrees Celsius, whatever. And talk after talk. And we went back through the literature and it's like almost every single experiment had just been doing that. And so we literally were sitting across from each other and just looked at each other and said, why does everyone just put a finger in? It's never the case that you just, have one finger in the cold. What happens if you do, if your whole hand was cold? And so that literally, when we went back to Slovenia after that workshop, we literally said, why don't we just do the simplest CIVD study out there? We just put our hand in cold water, except we put thermocouples on every finger and on both hands to look at whether there is kind of a contralateral effect, to look at whether we reliably get CIVD in multiple fingers at the same time. Why did everyone do that? We went back through the literature, and the reason why everyone just did it with one finger, and this was all the way up to 2005, while people were doing that, was because that's what Sir Thomas Lewis did in 1930 in the original paper that reported CIVD. And it was literally a case of monkey see, monkey do. And so when Igor and I did those studies, we showed that, just because there's CIVD in one finger does not mean that there's CIVD in the other. And, so that was already showing that spatial patterning was also important when we're looking at central control versus peripheral control. And we furthered some work on that. We've also looked at again, is there more than that classic CIVD pattern? And again, everybody shows that because, that's exactly what Sir Thomas Lewis showed. And this is the only kind of CIVD pattern out there. And we showed that there was way more than that one classic on off. So sometimes coming up with these ideas is really just going back to the drawing board and saying, like, why do people do it this way? And why do people look at it this way? Another example I've had was in 2015, we published a study looking at hydration and exercise in the heat. And all of the hydration literature up to that point has been, one day the participant comes in, they get a water bottle to drink. Another day they come in and they don't. And we were seeing over the past 20, 25 years, so much of the psychological influence on exercise that, again, I literally just sat around with my lab members one day and says, like, there's already, if I didn't get a water bottle, my brain is already messed up. So why don't we try to blind our hydration status? And so we came up with a way to blind hydration status. We were actually the first one to do it. And our initial study in 2015 suggested there was no impact of dehydration when you were blinded to the hydration status in the heat. And that led to, again, a change in the field. Most of the hydration research now will try to blind the study. There's been a number of papers that have came out after mine where, you know, they were really testing the thing. Some shows different results, some still show impairment, and that's completely fine. But that's how science advances, right? It's by people taking the risk to question dogma, so to speak. So a lot of times it's just going like, just because. So for example, if you were a grad student, you know, don't think of what is written down in the articles as gospel, right? It is still, feel free to question that. Why is it done this way? Or, you know, what would the results be if, you know, I tried it this way? So don't be afraid of that either.
Maybe we can do one more quick question. It sounds like an application. So do you recommend different training techniques for outdoor winter sports regarding time or intensity? Maybe given some of the data that you showed today with performance in the cold.
Yeah, I think just like with exercising in the heat, I think exercising in the cold, you do need to adapt to it. And there is a process of adaptation. I think in the cold, it tends to be more habituation and a mental adaptation to cold, which really explains why, you know, now, again, first day of snow, everything feels cold. But, you know, this temperature in 2 weeks time, 3 weeks time, you know, feels like nothing at all. When it's like this in the spring, you're already out in the barbecue with shorts and a t-shirt already. So a lot of it is that initial habituation in the cold, whereas in the heat, there tends to be more actual kind of physiology going on early on that drives the changes. But certainly long term, there are physiological changes, especially in these really sustained cold kind of survival type situations. But in terms of exercise and duration in the heat, in the cold, I would take the same approach of just gradually build up as if you were kind of forming heat adaptation camp and get used to it, because there's also a lot of discomfort initially if you are breathing in very cold, dry air. And again, you need to habituate to that discomfort. And but otherwise, I think you just need to keep your fuel stores high in the cold, and I think you can adapt just as well, you know, as you typically kind of can just in a normal training block.
Great. Well, thank you so much, Dr. Cheung. I appreciate your time. Nellie, do you have anything to say before we sign off here?
Nope, I was going to do just that. So thank you.
Okay. Thank you so much. I appreciate everybody attending, Dr. Cheung especially. Thank you for taking time out of your Monday evening to be with us. Hopefully everybody will tune in for our third one in a little while, mid-November. So yeah, I think so. So everybody, thank you again for attending, and we'll hopefully see everybody soon. Thank you.
All right. Thanks again.
Thanks.